Okay, so, let me look one thing up. So let's first talk about what's coming up on the schedule. Our final is scheduled for Friday of finals week, the 15th at 8 o'clock. And the difficulty is our thermo final is scheduled for the next block, the same day, starting at 11 o'clock. It really wouldn't be too bad just to take those tests because you're going to be out of the statics test in an hour and a half, and so you'd have time to sort of rest and look stuff over, but it wouldn't be ideal for studying. So I'm happy to make other, options available to people. People who don't want to do both of those back to back like that. So please just get in touch with me if you want to change that, and we can change it, okay? One or the other, not both, please. Okay, so let's think about this. So we have exam 3 is this next class period, Friday, 12/8. And the topics for that are going to be everything up until friction, everything except friction. There's definitely going to be something related to structures. And something related to internal loads. But you should be ready for anything that happened before that too. With statics, since everything that comes before basically goes into everything that comes after, it's hard to imagine me writing any test that wasn't just internal loads and structures. I mean, that sort of covers it all. So, yeah, I'd say be ready for that. Internal loads and structures. And then exam 4, the final, is Friday, 12/15, 8 to, it says it's scheduled from 8 to 11, but 2 hours is way more than enough time for what this test will be. But notice that for the people who are also taking thermo, the thermo final is also scheduled for that same day, Friday, 12/15, from 11 to 1. So contact me if you want to change one of those. I'm super willing to accommodate that. Okay.
You said Thursday and Tuesday, right?
Oh, the days that I have other tests?
Yeah.
Yeah, Monday at 11 and Thursday at 11 are when I have other tests, but I can do it outside of those too. But yeah, if you are willing to take it, if it worked out for you to take it with one of my other classes, that would be amazing.
Yeah. Yeah, cool. Because I'll probably take it on Thursday.
Okay, great.
Thursday?
Yeah, Thursday at 11 is one of them. But contact me either way because I need to tell you what the classroom is.
And then I'll just pretend like I was in that class the whole time.
Yeah. I'll just it's college physics. I'll just give everyone the thermo final. Or
You're just sobbing.
Yeah. I was not paying attention. I'd be like, actually, both can be true. This is not the right test, and you weren't paying attention. And then, sorry to do this to you, but I will not be here tomorrow or Friday. So that's not how you spell tomorrow. Tomorrow or Friday. But I do have all morning and all until like mid-afternoon on Friday available for Zoom meetings. So before I say that, no thermo class on Friday. There is the test on Friday, and that's going to be proctored for this class. But there's no thermo class Friday. So for the people in thermo, today is the last day of that. Okay? I am available for Zoom meetings Friday morning to 2 o'clock-ish, let's say. So just message me and I'll send you a Zoom link.
There's no regular class called.
Right. Next week is only finals week. So no classes. What?
I've never actually had an in-person final.
Oh, yeah, that's true. Yeah, that's crazy. Because of COVID.
Wait, I have never had one.
Yeah. That's so funny. Yeah, what a weird time. But anyways, we're going back to real school.
Real life?
Okay, so anybody have any questions about the stuff that's coming up? There's no more weekly assignments. I'm assigning one more statics problem. It's super quick and easy. But basically everything, the hay is in the barn. It's just getting ready for the tests and stuff. If you want to talk to me over Zoom on Friday, send me a message. And that's kind of all there is. Yep.
Will the final have friction in it?
Yes, there will be friction in the final, but it's not going to be like a huge chunk of it or anything. I'm going to talk about belt friction today. It's the last part of friction that we haven't done. I'm not making you derive anything for that. And I'm just going to show you how it works. That will not be on the final. It's easy. The reason it's not going to be on the final is because it's so easy. Like, okay. So let's finish up friction, and then once I finish talking about belt friction, then we can talk about whatever, go over an example problem. But going back to friction, we dealt with square threaded screws. and then bearing friction. And bearing friction was broken down into journal bearings and thrust bearings, B. And then the last one is belt friction. We're done with these, so now we just have to talk about belt friction. And the idea of belt friction is this. So think of Rapunzel. You know that story? Here's like a charming prince trying to climb up and visit this princess. And, you know, the way he climbs up is hangs onto her hair, unfortunately for her. Okay, so
Were you art mining?
yeah, this would not have scored very well. Okay, so this is a real bummer. You can imagine, for Rapunzel, this is a bummer. But instead, if she's smart, he can hang off of her hair like this, but there's luckily this pole here outside her window. And so what she does is she wraps her hair around this pole. And then she doesn't feel that force, okay? She feels a little bit of force, but a very small part of it. And so the weight of the prince doesn't change. The tension on his end of that cable is still just the prince's weight. But the friction of her hair wrapping around this pole allows her head to take a very small part of that force to support it. Okay, so there's always this going to be this tension in the cable. That's going to be T2 for what we're going to do. That's a bigger force. That's the required force. You can't get away from that. The prince weighs what he weighs, you know. But then by wrapping the belt or the cable around something, and it doesn't have to be a full time around, it can just be partial or whatever. The tension on the other side of the support is going to be smaller. And you can think of that as like what's required to support this, to keep it in equilibrium. The derivation of this isn't like super hard to understand or anything, but it just goes on and on and on. So I'm just gonna give you the formula, tell you how to calculate it, and this stuff, you don't have to worry about it after you leave here today, okay? Just remember that this is a thing you can do. It's not gonna be on the final or anything, okay? But the way this works is, if you imagine a top-down view of that pole, then there's the support that the cable is going over. The cable covers some amount of that support. This is the T2, let's say. This is the force that's bigger. And this is the force that you're trying to, withstand, keep in equilibrium. This is the one that you're trying to get as small as possible. And this is just the one that you're required to apply in order to keep this in static equilibrium. And you can think of the amount that this cable covers that support in terms of an angle, beta. So this, if you think of these as the points where that cable leaves the support, this angle is beta. Then the formula says the ratio of T2 to T1. Okay, is that ratio bigger or smaller than 1?
Bigger.
Bigger, yep. Is equal to E to the power of coefficient of friction times that angle beta. This beta has to be in radians. This is the coefficient of friction. Almost always in this case, this would be static friction because there's the belt isn't sliding on that. And so this is the formula. And notice that beta can be greater than 2 pi. So I have it as if it's not completely wrapped, it's just held around the outside. But you could wrap this around and around and around, and you could have your beta be 8 pi if it's wrapped around 4 times, okay? Okay, so let's see this work. So let's say that you have a pulley hanging from the ceiling. And one side of, so this cable goes over this pulley. And there's a force of 100 newtons that needs to be supported by this force F. What's the force F? First, if the pulley is frictionless, and second, if the pulley, like, it's not a pulley at all, say, it's just a support, or you can think of that pulley as being rusted all the way so it can't move. And the coefficient of static friction between the cable and the pulley is 0.1. So we're going to see what's the difference in these two cases. In the first case, if pulley is frictionless, well, what's that force going to be?
100.
It's just going to be 100, yeah. It's the same cable. So F is equal to 100 newtons. So now let's think of this in terms of belt friction. On this side, it leaves the pulley here, and this force is 100. On this side, we have this force F. The cable wraps around this support. And so what's this angle?
Pi.
Yeah, that's right. So beta is equal to pi. And so which one of these is our T2 and which one is our T1?
T2 is 100.
That's right, yep. So 100 over F is equal to E to the 0.1 pi. So, you know, that's E to the 0.314. And so F is equal to 100. I guess I can write this as times E to the negative 0.314. And what do you get for that? Can someone calculate that?
I got 73.2.
73 point what?
04.
0.04 newtons. So 0.1 is a pretty low coefficient of friction. That's, you know, slides pretty easily, but takes off a quarter. Yep.
If you have multiple pulleys, is it just the sum of each one?
Let me think about that. Yes, your force F on the first pulley would be your force T2 on the second pulley, and yeah, you just sort of keep piggybacking. That's right. Okay, let's do one more thing where now let's say that. What if you wrap it around 3 times? Okay. So what does it look like in this case? Well, here's our force of 100 newtons. And it's going to go around once, that's 2 pi. Twice, 4 pi. 3 times, 6 pi. And then it's going to wrap around another half time to get to the other side. And so it's going to go around, beta is equal to 7 pi. So 100 over F is equal to E to the 0.1 times 7 pi. And so F is equal to 100 E to the negative 0.7 pi. And what do you get for that?
11.09.
11.09. So at that point, you're getting a pretty small fraction of your original force.
So radius of the pulley doesn't really matter in this case?
The radius does not matter. Yeah, it's funny.
Derivation, does it like show up and then it eventually just falls off?
No, it never shows up because it shows up as a, I can kind of sketch how it works, but you take an infinitesimal piece of this cable and it's a wedge. Obviously, this isn't infinitesimal, but you think of this as like some small amount of angle. That's not an angle, that's a Q. But some small amount of an angle. Okay. And then that has an effect on what these angles are. Here you have your tension plus some small amount of tension. Here you have your T. Ooh, that looks like a delicious pizza. And then you have your acting this way. You also have your friction force acting this way. This would be this times some increment, some infinitesimal normal force. Here you have your normal force. Then you go through Newton's laws and you end up with a differential equation when you take your small angle. So you end up with a bunch of sines and cosines. You approximate your sines as, remember, when you have a small, if you take a limit of this as your delta theta goes to 0. Remember, sines of small angles, as you take the limit, as that angle gets smaller, approaches the angle. This is something that's really useful in a lot of these kind of derivations. So if you take your limit as delta theta goes to 0, sine of delta theta approaches delta theta. And as you take your limit, as this goes to 0, cosine of delta theta goes to 1. And that makes a bunch of stuff drop out, and you have, and anything that's small infinitesimal things multiplied together drops out because it's nonlinear. It drops out a lot faster than the linear terms. And you end up with this differential equation. Then you integrate it, and that's where you get the, yeah, that's how the derivation goes. But,
Yeah, just this kind of like we went over it.
yeah, it's a,
Before.
yes, it's a pretty common, it's a pretty common looking derivation actually when you, from mechanics.
Does this only work for circular objects too? Like say it's like a square pole. Like I don't know, and then you wrap the cable around that. Like
I don't know, but my hunch is that it does not depend on that because we're always assuming with these friction things that the only thing, so all of this is, all of the friction stuff we've done is based on this dry friction assumption that the force of friction is just equal to the coefficient times the normal. And that's a pretty questionable assumption, you know? I mean, what that's saying is if you have a block of wood and you apply 100 newtons of force down on the table, it's the same friction force if you try to slide it as if you have a 20-foot long 2x4 of that same amount of wood and you press down with the same force and try to slide it. That's not a very accurate approximation. It's a very rough guess at how friction works. But using that approximation, I would think that for an ellipse it would be the same because all you're really changing is how much distance you cover to get to that same angle. That's my guess. Any other questions about this? So, okay, I said that you could forget about this as soon as you leave here. I am going to make you do one super quick, easy question doing this, but this stuff will not be on the final, so you don't have to like study this or anything. The other friction stuff is, you know, fair game for the final, so you should be sure you can follow those sort of quick derivations from the other things. Yes?
So belt friction won't be on the final.
Belt friction will not be on the final. That's right.
But then we wish it was.
Yeah, you wish it was, I guess, right? Well, if it was, maybe I'd make you go through the derivation and then you'd wish it wasn't again. So I don't know. It's just a bunch of stuff that happened. It's not really, doesn't really have a major storyline.
I like the derivation because it like
Yeah.
it makes all the algebra tricks that you learned like feel worthwhile.
Yeah.
Like,
I agree. I mean, I think the derivations are, and the thing is, you start to recognize, like, you start to see a derivation happening for something, and you're like, oh, I've seen this 5 times before. This is a little different. This is a little different, but it's basically following this idea, you know. Yeah. Any other questions about that? Well, care to go over, I could do a couple of the kind of friction problems that will be on the final. I could write a couple of those up and let you work through those, and let's do that.
Go to the office today.
Okay, so let's say we have a square threaded screw. Let's say that the coefficient of friction is 0.05. Let's say that's the coefficient of static friction. And let's say that the lead is 0.004 meters. And the radius of the screw is 0.02 meters. So if this screw supports a load of 2,000 newtons, what's the required couple that you have to apply to that screw to initiate motion of this weight down? Okay, so see if you can think through that. Ask me if you get stuck, or talk to each other if you get stuck. A normal force up. A friction force, since we're talking about moving this down the ramp, the friction force is going to counteract that, so it's this way, 0.05 N. And this force Q that we're applying is this way. So first we can figure out the angle. The angle is, so if you think of straightening out that thread for one revolution around, we have a lead of 0.004. And the horizontal length is 2 pi r, so 2 pi 0.02. And we can use that to find the angle. And so the inverse tangent of the angle is 0.004 over 2 pi times 0.02. And so what do you get for that theta? Anyone get that?
1.8 something.
1.8?
1.823.
1.82 degrees.
Yep.
Okay, so now we can use this to come up with our rotation matrix. You can do this with trigonometry too if you'd like. So we got cosine of 1.82, sine of 1.82, negative sine of 1.82, cosine of 1.82. And you get a rotation matrix of 0.9995, 0.0318, negative 0.0318, 0.9995. And now we're just expressing all of the forces in the free body diagram in this rotated coordinate system. So we can go this thing times that force Q would be negative Q0. So if you multiply those out, you get negative 0.9995 Q and negative 0.0318 Q. Then the weight force.
For that rotation matrix,
Mhm.
I got the first one was negative, and then the second one was not negative.
Let me see. I
may have entered it in wrong, but for the Q
yeah.
force rotation had a positive coefficient for the x component, or a negative for the x component, and a positive for the y component.
For the Q force?
Yeah, so in the bottom line there,
You had the same matrix?
I believe so.
Yes, that should be. Well, okay, you had a negative for which one?
For the bottom, for only negative for the x component.
You're right about that. That's what it should be, yes. I did. So that's a double negative. You're right. That's how it should come out. And then for the second one, I got negative 63.52, negative 1998.99. The other ones are aligned with the coordinate axes, so we don't have to mess with those. So then Newton's second law says 0.9995 Q, 0.0318 Q, plus negative 63.52, negative 1998.99. The coordinate system I'm using is like this. So you can see the friction force is in the positive x, the normal force is in the positive y. these add up to 0. And so our system of equations says negative 0.9995 Q plus 0.05 N is equal to positive 63.52. And then our second equation, 0.0318 Q plus N is equal to 1998.99. My calculator just ran out of batteries. Is that the equation you got? And what did you get for the values?
I got Q equals 36.33 and N equals 1,997.9.
36 point what?
33.
33 newtons. N is equal to basically 2,000.
Yeah.
What was it?
1997.9.
1997.9. Okay. And then the last step is I asked for the couple, not that force Q that you'd get from pushing on the back of the thread. And so that couple is equal to Q times R. And so this is equal to 36.33 times 0.02. And what do you get for that?
I got 0.73.
0.73 Newton meters. Any questions about that? What would be different if I asked you what couple was required to initiate motion up the ramp? Yeah, question for, yeah.
So for the exam, you want us to go through the whole derivation, or is it
Yeah, I want you to go through
the whole
the
triangle?
derivation. If you don't want to use the rotation matrix, feel free to just use trigonometry, but yeah, I want you to derive this. What?
You want to see the whole?
Yeah, I do. Yep. And then what would change if I said we wanted to initiate motion up the ramp?
The sign of Q and
Q would be the other direction, and the friction would be the other direction. And you get a slightly bigger value because you'd be fighting against gravity instead of gravity helping you a little. Although it wouldn't be much different in this case because that's such a shallow angle. Yeah. Okay, that's all.